My name is Jose Coves, and today I'm going to talk about one byte overflows. Okay, so in this presentation, I'm going to start with a quick demo just to make sure everybody understands how this really works and to sort of like show you how this works. After that, I'll have an explanation of how this demo worked and why it worked. And finally, I'll conclude with some tips on how can we protect ourselves against this kind of attack. Okay, so let's go ahead with the demo. So here we have a vulnerable program. As we can see, this program takes a buffer of size 512 and then it just copies the input, but there's no checking. So we can just have a regular buffer overflow, and if we execute this buffer overflow with the shellcode, we'll see how this program is indeed vulnerable. So, and indeed we have spawned a shell. So now let's try to do a fix for this program. So if we actually fix it, we'll by checking the length. So if the length is greater than the size, then that will cause an overflow, right? So let's fix this. Is this program still vulnerable? Well, let's see what happens. So if we actually just type 812, which is the size of the buffer, we'll find something interesting. Oh, we have a segmentation fault. Why could it be? Let's go into GDB and explore why this might be happening. Okay, so very quickly, I'm gonna set two convenient breakpoints before and after the data has been taken from the input. So as we can see on the first one, the ABP right now is perfectly fine. So right now I still haven't taken the input of all A's, but now the input has been taken. We have printed the input of all 512 A's, and if we look now at the ABP, we can see how indeed the null byte, the terminating null byte for the 512 A's, has corrupted the EBP, which now ends in with the null byte instead of B8. So can we take advantage of this exploit? Yes, we actually can. So here I have crafted an exploit which still uses the shellcode, but the difference is that now we still have all the A's at the beginning, but now what we're doing is noticing that since we're writing a 0 into the null byte, then we're gonna go back into the ABP is now gonna be smaller. So it's going to be inside our buffer, which means that when main returns, we'll actually go back. So here is where we actually need to put the return address that before we had simply at the end. We now have it over here, and that's where we'll jump to our shellcode followed by an opcode. So if I just exit, if I just go and run that, we'll see how it is indeed vulnerable. So let's see, and yes, we are indeed in. And now that we're here, we can do nasty stuff like, ooh, let me see, what can I do over here? Oh, what's going on? Yes, we can eject the CD-ROM, or we can, I don't know, maybe look at the grades for the class. Seems like everybody's getting an A. Well, you won't hear me disagree with that. But all this is very fun, but let's see more in depth why this happened and why this was successful. So, okay, let's go. So at the beginning, we just have our main with the return, the EIP and the ABP, and then as we enter the function, which has the string copy, we'll just have a bunch of A's. Here we have the address of our shellcode, here the knobs, our shellcode, and more A's. And this is where the EBP is positioned, where the previous stack pointer was before entering this function, and now the stack pointer. As we do the leaf, so by the way, the stack is growing from the top, so this is the top and it's growing down, and the buffer, we start writing here, but the buffer grows up. So this null byte is inserted here in the least significant byte of the EBP. So here, the EBP is actually now terminating with a 0. And as we leave sub, since the EBP, which was supposed to be pointing here, has been corrupted, this one, now the ABP is going to be pointing to the middle of our buffer. How do we take advantage of that? Well, not yet, because remember, this is the ABP. Unlike the regular buffer overflow, this is not the EIP, so we can't actually jump yet into our shellcode. We don't know where this is going to happen. And this is not executed. This is still the ABP. So when when our subroutine actually returns, then the then the main actually leaves. We'll see how the stack pointer is now pointing right under our so in our buffer, right under the address of our shellcode. So when main actually returns, because main actually also has to end, then that will interpret that it'll try to pop the EIP, this address, which it'll think it's the previous return address, into the AP, and that will indeed be the address of our shellcode, which will lead to execute all the NOPS instructions and our shellcode, hence spawning the shell. Now, let's see how can we protect ourselves against this kind of attack. So the main protective countermeasures involve using a safer programming language, using also safer libraries, protections against buffer overflow in general, not just one byte overflow. And these also include executable space and address space layer randomization. We've covered some of these in class, but here I'll try to actually explain how they relate specifically to one byte buffer overflow. So the programming language is actually important, even though almost all languages have some sort of vulnerability. C and C++ are explicitly vulnerable to this kind of attack because they allow direct access to memory as well, and they're not a strongly typed language. They have no built-in protections and they have no boundary checks, so you can call an array with an index that's greater than its size. Java and Python, however, have no direct access to memory. They're strongly typed. They don't allow you to go out of bounds, and they also have this compile time checking. Also, many interpreted languages like Lisp have signaling that will signal these error conditions. Another approach would be to use safer libraries. So the dangerous ones are the ones that involve no boundary checking, like gets, scanf, string copy without the length. So these ones will just copy until they find the terminating null byte, but we don't know how long that could be. That's why we have to actually use the length constraint, like using string copy, for example, with the end. However, this one does not guarantee the string to be null terminated, since it will copy n bytes. So that's why it's not entirely recommended, and it might be better, unless you use with the right size, it might be better instead to use string L copy and string L cat. Also, there are other libraries like the better string library that are designed with this idea in mind. Finally, buffer overflow protections are important. We can detect corruption by the canary method, which consists in inserting a random cookie after the ABP, and before we return, we check that the value has not changed. We can also split the stack in two, one for the data and one for the function return information like the ABP and EAP, to avoid this kind of corruption. And finally, we can also limit the executable space to make sure that we can either write or execute a specific memory segment, but not both. That way, injected data will not be executed. This is, however, vulnerable to attacks like return to libc, and we could probably address this by using address space layer randomization, which makes hard to guess the address of libraries and instructions by randomizing where they're located. This makes it harder, but this doesn't guarantee a fix. If the program is vulnerable, ASLR will not fix it. It will just make it harder. So I hope you guys have learned how to execute and protect yourselves against one byte overflow attack. Thank you very much. These are the references. I hope everybody has a good day. Thank you.